Hello. On behalf of the Planning Committee, thank you all for coming to tonight's event, Wise in 3 Acts, Past, Present, and Future. We have a wonderful evening planned, and we are so pleased that you are here with us tonight to be a part of celebrating women in science and engineering. My name is Samantha Tuchman, and I'm in Sociology and Women in Gender Studies, and I am the WISE Acadia Student Executive Member representing Women and Gender Studies students. My role in WISE is to support and emphasize the A in STEAM. Arts and humanities teaches us skills such as creativity, design thinking, communication, and power structures, all of which make us better scientists. We've designed the program this evening in 3 acts: Wise Past, Wise Present, and Wise Future, more of which we will learn about shortly. But to begin our night, I'd like to welcome Dr. Wanda Campbell from the English department to begin our celebration with the reading of the poem Power by Adrienne Rich. We'll also hear from Dr. Campbell later in the program as she shares with us an original poem.
The American poet and public intellectual Adrienne Rich wrote her poem Power about Marie Curie, the first woman to win a Nobel Prize and the only person to win a Nobel Prize in 2 different sciences, for physics in 1903 and chemistry in 1911. Power. Living in the earth deposits of our history. Today, a backhoe divulged out of a crumbling flank of earth, one bottle, amber, perfect, 100-year-old cure for fever or melancholy, a tonic for living on this earth in the winters of this climate. Today, I was reading about Marie Curie. She must have known she suffered from radiation sickness, her body bombarded for years by the element she had purified. It seemed she denied to the end the source of the cataracts on her eyes, the cracked and suppurating skin of her finger ends, till she could no longer hold a test tube or a pencil. She died a famous woman, denying her wounds came from the same source as her power.
Thank you, Wanda, for starting our celebration with that inspiring reading of the poem Power by Adrienne Rich. So this event came to be when members of the WISE Acadia student were having an informal discussion on all of the wonderful achievements and rightful recognition currently happening for women in science and engineering right now. Both at the international and national level. Among these scientific achievements including the American chemist Dr. Frances Arnold winning the Nobel Prize in Chemistry, and the Canadian physicist Dr. Donna Strickland from University of Waterloo winning the Nobel Prize in Physics. At Acadia University, we can also celebrate because we have the appointment of the first female Dean of Science, Dr. Suzie Currie, who we are going to have the pleasure of hearing from tonight. And we decided what a better way to acknowledge all of these achievements and to honor our past than with a celebration and some cake, which we'll be having later. And as Sam Tuchman indicated, the event is called Wise in 3 Acts. So tonight we will be telling stories about some of the past history of women in science, including information on past Nobel winners and some should have been past Nobel winners, including their stories of resilience. The present act will include this year's 2 female Nobel Prize winners, and not just their stories, but also an explanation of the science behind their work, because it's important to recognize women and their actual recognition of the scientific contribution. And Anna Kiefte from the physics department will be talking about Dr. Strickland's Nobel Prize winning work, and Dr. Elizabeth Gillis from the chemistry department will be speaking to the Nobel Prize winning work done by Dr. Frances Arnold. And Dr. Suzie Currie will then lead us from present into the future, and followed by a second poetry reading by Dr. Campbell and closing remarks from Yvonne Lyon, our president of WISE students. we encourage you to talk about all of these 3 acts and discuss after our presentation at the mingling session, which we believe is really important because just as this event arose with informal discussion on issues and topics, we can have so much more wonderful things happen after the event as well. So it's my pleasure to introduce Dr. Randi Lynn Newman, professor from the psychology department here at Acadia University, to discuss and share a story of the importance of recognizing that women have always been scientists, and to put into context the progress that has been made in giving women in science and engineering the recognition that it's deserved.
Thank you for having me. One of my favorite parts of course that I teach is talking about the history of women in science and of telling stories about their life, their contributions, and just how important it is to recognize them. So I'm presenting Act 1, the past, and just to get us to the past, I want to just put into context a little bit about the significance of the wins that were announced on October 2nd and October 3rd of this year. So on October 1st, headlines, so I have a lot of headlines here in this talk, and on October 1st, the headlines that dominated, particularly newspapers in Europe, and that dominated some of the Twitterverse on that weekend, came from, it was a conference actually, a workshop in Geneva on gender and high energy physics that an Italian physicist and a CERN scientist, Alessandro Strumia, was presenting at. And in his talk, Professor Strumia told the audience that, men built and invented physics, and that it was by invitation only, and that you basically had to prove yourself to call yourself a physicist. He also then presented largely what I'll call his feelings, not facts, on sort of this notion that women aren't actually suited to study physics. On the same day that this article appeared, Jess Wade, who is a physicist that does spend some time at CERN, she's a postdoctoral research associate at Imperial College London. She wrote this headline reacting to Professor Strumia's talk. It says, "It is 2018. Why are we still debating whether women can do physics?" Well, I don't know how Professor Strumia felt about karma, but on October the 2nd, it was announced, the day after, that Dr. Donna Strickland had won a Nobel Prize in physics. And we're going to hear about that important work. The prize that she shared with her doctoral advisor was on chirped pulse amplification. The headlines that day, that they all sort of make reference to the historic nature of this win. That she was only the 3rd woman to have received the Nobel Prize in physics. That she was the first woman to receive the Nobel Prize in physics in 55 years. Who is Donna Strickland and why is she one of the few women to win a Nobel Prize? This is just a collection of some of the headlines that we saw that day. On the following day, October 3rd, and I was sending this sort of very early in the morning to Barb and Sam, and I think Glennis as well, I sent these to. And then on October the 3rd, we wake up and we find out that Dr. Frances Arnold, a chemist at Caltech, she's a chemical engineer, she had won the Nobel Prize in chemistry. And this was only the 5th time in history that a woman had received the Nobel Prize in chemistry. And so again, the headlines are quite similar, right? That she's, mentioning she's a woman and the historical nature of this win. And so we pause and we ask ourselves, why do these headlines, why are they reflecting on this notion of it being such a historic win, and in particular as it related to women in science. So, you know, this graph is meant to sort of highlight for you why that win was so significant. So, you know, between the three science prizes that are given out, physiology or medicine, chemistry and physics, we've had over 600 Nobel laureates. I think it's 607, I think. And of those, only 18 prizes have been awarded to women, to 17 different women, because as Wanda said, Marie Curie won for both physics and she won for chemistry. We've had 12 Nobel laureates in physiology and medicine, 5 in chemistry, and only 3 in physics. When we look at a graph like this and we say, you know, why, you know, at least I do, why do we see such a gender gap? It would be tempting to say, and I've certainly, you know, heard this type of response, well, I mean, you know, women just weren't doing science back in, you know, early turn of the century, right? You know, that the percentage of women has always been low in areas of physics and chemistry. And while we can't deny that the percentage of women who've studied, particularly in chemistry, is lower than that of men, there's no question that women were always doing science. And that was reflected in, again, after these two wins, Jess Wade, who had made that comment about Dr. Strumia's talk, was interviewed. And what she said really hit home for me, because what she said was that it feels like the world is waking up to the ingenuity of women scientists. And, you know, when the full interview that she gave really sort of underscores this notion that women were always doing science, and that explanations for this gender gap in Nobel laureates can't simply be distilled down to the percentage of women doing the science, but rather that the contributions that women have always made to these disciplines and many others have been undervalued, and in many cases actually misrepresented, or you have a number of examples where supervisors took credit, you know, for the work of female scientists. You have examples of female scientists who weren't permitted to actually publish in their own name because publishers would not publish a female scientist's name. An example from our discipline of psychology is Lillian Gilbreth, sort of the mother of industrial organizational psychology. And she had to publish much of her research under her husband Frank's name. And when she finally did publish one of her most important works, the publisher agreed to put her name on it, but only if it was just her initials, L.M. Gilbreth. So we see these contributions not just being undervalued, but we don't even realize that it's been a female that has been contributing to much of that work. Now, you know, in my class we do talk about challenges when we talk about barriers, but one of the things I think is important to recognize is the progress that we've made. And Dr. Strickland talked about that after her win. And she in particular made mention of the two women who won Nobel Prizes in physics prior to her, Dr. Marie Curie and Dr. Maria Goldbert-Meyer. And so let me just tell you a little bit about these two women. Their stories are extraordinary, really, but and it would take me all night just to adequately talk about Dr. Marie Curie. She's a household name today. Dr. Mockford and I were talking about that. If I said name a scientist, she would be one that many of us would think of, and is often actually the only female scientist that people in a non-academic audience will think of. You know, as Wanda said, she was the first woman to win a Nobel Prize. She's the only person to have a Nobel Prize in 2 science categories. And fun Nobel Prize trivia, her daughter Irene also has a Nobel Prize, and Irene's husband also has a Nobel Prize. Those family gatherings, as Steve and I said, must have been something. You know, as this quote, I'm not sure if you can see it, but the quote from Dr. Curie is, "I was taught that the way of progress is neither swift nor easy." And certainly, you know, the progress and her success was not easy. She didn't enter university until she was 24. Her mom had died when she was quite young, and she worked as a governess to support her sister through medical school. And when she went to university, she actually felt really ill-prepared in math. And so that was a focus of hers, was to ensure that she was keeping up, and of course, you know, she did. After graduating with her PhD, she worked as Pierre Curie. They would get married, but she worked as his unpaid research assistant, and that's a theme that we talked about. You know, that we talk about in my class. Many of these women worked up until the 1950s and 60s in voluntary positions, voluntary unpaid professorships. Right, in dingy, dark basements or attics, literally. She left Pierre at one point because she thought there was an opportunity for her at Krakow University. This was before they were married, but she ended up being denied that position on the basis of her gender, on being a woman. So she went back. She was Pierre's unpaid research assistant. They did become married. Pierre became actually really quite swept up in her research because he recognized that she was really onto something important, really groundbreaking. And of course, that was realized when in 1903, both Pierre and Marie shared the Nobel Prize for their work on the theory of radioactivity. But I'll mention that her name was actually not originally on the prize. And Pierre actually advocated for her and said he refused to accept the prize if her name was not rightfully put on it. And so the president of the Swedish Academy sort of resigned, you know, not resigned, but he accepted Pierre's argument, and she did receive that prize. But at the address, at the formal address where they received the Nobel Prize, the president of the Swedish Academy said, "It is not good that man should be alone. I will make a helpmeet for him." The notion that, again, her contributions are being undervalued and she was nothing more than as an assistant, essentially riding in the coattails of her husband. She didn't receive a paid position until Pierre was killed in 1906. Her appointment was at the Sorbonne, and she was appointed as an assistant professor, even though she had won a Nobel Prize. She would go on to receive another Nobel Prize in 1911. Even that was met with opposition from other scientists, and this prize was in chemistry for her discovery of radium and polonium. Dr. Maria Goeppert Meyer, also a physicist and a Nobel laureate, now 60 years after Marie won the first prize in physics, she would be presented. Her prize was for her work on proposing the nuclear shell model of the atomic nucleus. And, her story, too, is so interesting. Like Marie Curie, she worked as an unpaid assistant for almost her entire career, from the early 1930s it wasn't until actually 1960 that she had a paid appointment at a university. By this point, she had already done the research that she would receive the Nobel Prize for. Her husband was Joseph Meyer, was also a physicist. He accepted a position at Johns Hopkins University, believing that this would provide both of them with a lab, with a position to do their research. But Johns Hopkins developed a rule, a policy that actually prevented wives of husbands from being appointed at the university. Joseph would eventually leave there. They went to Chicago, first to Columbia University, then to Chicago, where she was a voluntary research or associate professor, so she was unpaid. But she had made important connections with Edward Teller, who won a Nobel Prize. She actually worked on the Manhattan Project, the creation of the atomic bomb. And that work led her to getting this paid position at the University of California. And you know, when she did win the Nobel Prize in 1963, I thought it was interesting. I actually found this headline in the newspaper, a clipping from the newspaper, and it says, SD means San Diego. San Diego mother wins Nobel Physics Prize. And it's hard to see, but underneath that, they actually comment about her red hair. And, you know, which has nothing to do with the science, and certainly when Teller won his prize, I'm pretty sure they didn't mention that he was the father. And the quote here says, when you love science, all you really want is to keep working. And so, you know, I always tell my students that, you know, these women, these scientists really represent to me, you know, resiliency, not that we should have to deal with the level of obstacles that they did, but they were certainly resilient and passionate about their science. And Dr. Rita Levi-Montalcini, I know Dr. Gibson, this is one of Dr. Gibson's favorite scientists. Dr. Gibson talked about Dr. Montalcini in my class last year, and the favorite of the students. She won the Nobel Prize in 1986 for discovering nerve growth factor. It's a protein that keeps our neurons healthy. And, you know, what did she face that was challenging? Well, she was a Jewish individual, and after graduating with honors from medical school, because Mussolini was head of government in Italy, Jewish individuals were banned from practicing medicine, banned from participating in research. So her family actually had to go into hiding. But she didn't stop her to those embryos. She discovered how motor neurons grow and die, and then after getting into a lab environment again was when she discovered nerve growth factor. So again, someone that made really critical contributions to science, and this quote actually was within my email signature because it is one of my favorites. Above all, don't fear difficult moments, the best come from them. And she lived into her, she was 102 or 103 when she died, just in 2012. So, you know, these are women that did win the Nobel Prize, but there are many, many others that, you know, were essentially snubbed by the Nobel Committee. One of them is Lise Meitner. Lise Meitner, again, you know, a Jewish individual who had to flee Berlin. She, at the time, was working with a collaborator, Otto Hahn, and they were working on, you know, what is now known as nuclear fission, right? The nuclear reaction that produces nuclear energy. Even after she fled Germany, they continued to work and write each other back and forth. It's said that Otto Hahn didn't quite understand some of the theoretical implications of the experiments, but Lise did. She was a theoretical physicist, and it was her explanations that really provided sort of the critical understanding of the fission process. Unfortunately, though, again, she was overlooked for the Nobel Prize because in 1945, Otto Hahn was presented with the Nobel Prize in chemistry, overlooking Lise Meitner. And certainly, people looking back at this will say that she absolutely should have received the Nobel Prize in physics for her work. Another example that you know, many of you may now know Dr. Jocelyn Bell Burnell's name because she was in the paper not that long ago. Her story is also interesting. She is another physicist. You know, when she was in, I guess what would be considered our junior high, middle school age, girls weren't actually allowed to study in a science lab, right? And her parents put pressure. This is in the late 1950s, early 1960s. But her parents put pressure on the school until she was allowed. And when she went to university, she was the only woman in her physics class. She went to Glasgow for her undergrad, Cambridge for her PhD. And she says she explains there was a tradition at her university that every time a woman walked into the classroom, the men would whistle and bang on their desks, and not in a welcoming fashion, and also make comments on her appearance. And that pretty much happened to her every day. While studying for her PhD with Anthony Hewish, she discovered what Anthony Hewish thought was actually signals from aliens, but turned out to be pulsars, spinning stars made up of neutrons that throw up beams of radiation like a lighthouse. And because she was a woman and because she was a student, she was denied the Nobel Prize when Anthony Hewish, even though he thought they were aliens, she was denied the Nobel Prize. But Dr. Jocelyn Bell went on, she still is an esteemed physicist and astronomer, and she very recently, last few months, received the $3 million, I think that's American, Breakthrough Prize in Physics. And she gave it all away to support diversity programs in physics. And what she said is after winning this prize, increasing the diversity of physics could lead to all sorts of good things. Because she knows, just as Jess Wade knows, that really women have always been doing science. It's just people seem to just be waking up to that now. So many other examples. You know Katherine Johnson because of the movie Hidden Figures. She was a critical component of NASA's early days. She's the individual, she was the only woman on the engineering team that calculated the launch window and trajectory for Alan Shepard, the first American in space, and of course, personally checked the computer's math before John Glenn was sent into orbit. When I think back to Katherine Johnson's story, one of the things that comes to mind is something I read when I actually read Margot Lee Shetterly's book, Hidden Figures, of which the movie's based on. Margot's an African-American woman, and her father was a NASA scientist. Margot grew up thinking that all African-American women worked at NASA. Right? Representation matters, right? She grew up thinking that it was that all mathematicians were African-American women that worked at NASA. And that's because what she grew up with was seeing just that. The numbers of African-American women that did play such an important and critical role in NASA's space program. Dr. Brenda Milner, I can't talk about science if I don't talk about Dr. Brenda Milner, because she is the founder of my discipline, neuropsychology or cognitive neuroscience, some people would say. Dr. Brenda Milner's still living. She just turned 100 this August or September. I'm embarrassed. I celebrated her birthday. I should know the date. She transformed the study of mind and brain by studying the relationship between the physical brain and behavior, and particularly, how does our cognition and our behavior become impacted when the brain is damaged in some way or is in some way dysfunctional. So much of what we know about memory, so much of what we know about language is based on her work. And I just love this quote from Dr. Milner that says, "People think because I'm 98 years old that I must be emerita. Well, not at all. I'm still nosy, curious." And so, what you will be maybe surprised to know about Dr. Milner is she still goes to work 3 days a week at McGill University. She lives 10 minutes from campus and walks uphill. And so we can all think about that when we drive to work. She's thought to be the oldest scientist to ever have an active research grant and the oldest scientist to ever supervise a student. right? So she's remarkable. She's one of Canada's most esteemed scientists. She won the Gardner Medal in 2005. Many people who win the Gardner Medal go on to win the Nobel Prize. I'm still pulling for her, but you know, nominations to the Nobel Prize Committee are by invitation only, and I haven't been asked to if I could give a nomination yet. So, we have made significant progress, right? As Dr. Strickland noted when she won the Nobel Prize, you know, I have a paid position, unlike Curie did, unlike Goppert-Meyer. That's not to say that we don't have challenges, that we don't have significant barriers that I feel need to be removed, as you know, opposed to kind of trying to figure out how we're going to go around it or jump over it. Let's just get rid of them. But I think it's really important that when we're talking about recruiting and retaining talent, that one of the best ways that we do that is by telling stories, by taking time to talk about these women, past and present, and to tell their stories, to talk about their significant contributions, because that representation matters. Just like it matters, Dr. Currie, that you're here as our first Dean of Science. That matters. So as Dr. Strickland says, we need to celebrate women scientists because we're out there. Hopefully in time, it will start to move forward at a faster rate. Thank you.
Well, it's great to see you all, and I want to thank the organizers for inviting me to talk a little bit about Donna Strickland's work. As you can see here, I've purposely inserted the word "some of" here because I have 10 to 15 minutes, and clearly I'm not going to be able to give you a really thorough overview, but I'd like to give you a few sort of key points so that if you go to explore this topic further, that you'll have a starting point and you'll hopefully be able to read that and watch that with a little more clarity. So first off, I just wanted to draw your attention to the press release and just to mention that for this particular Nobel Prize, there were 3 winners. There was Arthur Ashkin, there was Gérard Mourou, and there was Donna Strickland. And of course, today we're going to focus on the project that Donna Strickland worked on and led as a PhD student. So the citation mentions a few things. So first off, for groundbreaking inventions in the field of laser physics, for the optical tweezers and their application to biological systems, and for their method of generating high-intensity, ultra-short pulses. So I'm going to focus on 2 aspects of this, just to focus on some things specifically related to Donna Strickland's work. So first off, I just want to draw your attention to the fact that LASER is actually an acronym, and it represents light amplification by stimulated emission of radiation. So first off, just to say that basically work that led to the lasers, the development of the laser, started in the late 19th and early 20th century through the strong development of understanding around atomic structure. And we were at that time also able to conceptualize the ideas of spontaneous emission, stimulated emission, and things like the photoelectric effect, which are related to this. In 1954, a maser was built, and basically a maser is a type of laser that's specific to the microwave part of the light spectrum. And as you know, the light spectrum is made up of all kinds of different light waves, some of which are visible and some of which aren't. So the maser was actually the first thing to be built. Back in 1958, the principle of the maser was extended to a larger part of the electromagnetic spectrum, and then the first laser itself was built in 1960. And the Nobel Prize was quickly awarded for that work in 1964, and there have been several Nobel Prizes awarded over the years for work related to lasers, and of course the most recent is this work that was completed by Donna Strickland. It's quite notable that the work that she won the Nobel for was completed while she was a PhD student in the 1980s and in Rochester, New York, which is not in Canada, but very close, as you know. So just to give a bit of a context of lasers and just, again, what makes lasers kind of special compared to some other light sources. So firstly, light coming from a laser is coherent. And what that really means is that the light lines up with itself perfectly. It's collimated, so light stays straight in a very narrow beam. And so here I have a red laser pointer, and you see that it ends up, even if it's going very far across the room, it stays in a nice narrow beam. It's monochromatic, which means it's a single color. And color in physics, and in science, is characterized by its wavelength or frequency. And it's very high intensity. So because it's distributed over a very small area, it's very intense, because intensity relates to power and area. So many of us in this room probably have a bit of context around atomic structure, but I just want, again, to contextualize so we're all at the same point. So atoms, are made up of electrons, protons, and neutrons. And electrons are as small as they can be, basically. And they exist, and they're weakly bound to the atomic nucleus. And the atomic nucleus contains neutrons and protons. And those neutrons and protons, in turn, are made of a bunch of other particles, and those particles are subatomic particles. And you've probably heard a lot about subatomic particles, like quarks and things like that. And those exist in the atomic nucleus. The electrons, the ones that are very, very, at low energy levels, are very, very strongly bound to the nucleus. And then when you get to higher energy levels, those electrons are more weakly bound. And when any energy is hitting hitting an atom, if the energy is of an appropriate level, it can hit electrons and make those electrons go to a higher energy state. When those electrons go to a lower energy state, the energy that's sort of released comes out in the form of a photon. And that's what we call spontaneous emission. So as long as you have a way to excite the atom appropriately, those electrons can get excited, and then they go back to their ground states, to their natural energy states, and they emit this light. So if we have more energy that's incident on this electron, it provides more energy to the system, and that makes that happen more. And basically you end up with a system called stimulated emission, where it's essentially sort of a chain reaction type of process. Not quite the chain reaction you would hear about in something in other physical properties or processes, but just to give the context that if you put more energy in, you get more energy out. And that's stimulated emission. And what happens is these photons that are emitted end up being coherent. And I already mentioned coherence, where those photons are perfectly aligned, essentially. So every atom has a different electronic structure, has a different atomic structure. So those electrons all exist in different energy states. So you can imagine a situation where you're exciting this atom. Those electrons are going to different energy states. They then go back to a lower energy state. They give off a photon. A photon has a certain color associated with it, associated with this energy that it has just jumped back down with, essentially. And so each atom emits different colors based on those energy levels. And so the color of light is associated with the type of atom that has that structure. And so we can tell a lot about the composition of a material based on what it emits. So in a laser, to be specific to the laser, each lasing material or lasing medium is excited, and it gives off a different color as a result. And it really depends on the application and what we're using the laser for. That's what determines what we want our lasing material to be. There's several kinds of lasers. I could say that they're cut into 4 main categories, what are called solid-state lasers, where we take something like a glass and we dope it. And when you use the term dope, what you're really doing is what you're really saying is that you're giving that material an imperfection, and that imperfection changes its properties. A crystalline material could be used. So an example is something like a ruby laser, ruby being essentially a type of glass. we use light to provide that excitation energy. Gas lasers are commonly used, so this laser right here, or this is the inside of a laser, which I'll show you in a moment, but this is a helium neon laser, or the insides of it, and that would be considered a gas laser. Liquid lasers, semiconductor lasers, these are all forms of, or types of lasers. And again, like I mentioned, depending on the kind of laser it is, it's hard to see the numbers, but you see that each of these types of lasers has a different wavelength. So in other words, has a different color. So specifically, Donna Strickland's work was done with a neodymium-doped yttrium aluminum garnet laser. So specifically, that is a type of solid-state laser. So looking at lasers, again, this is the inside of a laser, and I'll pass this around the room if you'd like to have a closer look at it. But all of the lasers have different technical details associated with them, but the fundamentals are pretty consistent. So what we have here, in this case, we have a lead over here, and we have a lead over here, and we would put this up, we would hook this up to an electronic source, so we put it against or across a voltage supply, like a battery kind of thing. So you put that electrical voltage across it, that excites the system, and inside is the gas, the helium neon gas, and that's going to excite the system. And on either end of the laser, you see that you have two mirrors. Those mirrors are going to cause reflections back and forth, and the light is going to come out of one end of that laser. In fact, it's technically going to come out the other side, but we set it up in such a way that it's really only going to come out one end. So you see all these general sort of features. Again, all of the details, the technical details are going to depend on the particular type of laser. So I'm just going to pass this around in case you want to have a look. All right. So going back to the work of Donna Strickland. Some lasers are set up to emit light continuously. So this little laser pointer emits light continuously. Some lasers are set up so that they emit pulses. And the laser that Donna Strickland was using emitted pulses. And the technology and the technique that they invented was called chirped pulse amplification. And I'd like to sort of go through a couple of aspects of this process, of this chirped pulse amplification process. So again, you have a bit of context. Basically, one of the reasons this was a very difficult invention, one of the reasons this was not a simple problem, was that a laser, in and of itself, could have a lot of energy. So if this laser was a very highly energetic laser, or a very intense laser, I should really say, I would be pressing, or I would make it go to the wall, and the wall would potentially, light on fire or something, right? So basically, a material can only handle so much energy. So if you took this signal coming from the laser and you put it into a material directly, it would basically fry that material. So what had to be done in this case was the signal, which was this short pulse that you're seeing on the upper left corner of the figure, it needed to be essentially spread out. So that little device that you see there, it's basically made up of two parts. It's made up of something called a diffraction grating, which is basically something that you have that is a sheet that has a bunch of little slices in it, and it's made up of a mirror. Again, details of exactly how that's made, let's just say that those are the two main important features of this. So the signal is spread out. It is then, by being stretched, that little piece of neodymium glass, that red piece in the middle of the figure, can handle that laser pulse, essentially, because it's been stretched. Then it's amplified. The amplifier material is sort of like the lasing material we were talking about before. It's making energy because of the process of, essentially, of stimulated emission. And then that amplified pulse goes back through another system, which is basically the backwards version of that first one. And by doing that, it's essentially narrowed again. And that's how we get a very large but very narrow pulse. So we have an amplified pulse, which is much more intense, and it's also very narrow. And I'll talk about why the narrowness is important in a moment. So the reason this was considered so important, first off, technologically it was difficult to do. Because if you just tried to create that initial intense pulse, number one, you wouldn't be able to create a pulse that was quite as intense. And number two, by trying to put it immediately into a material, you could essentially fry the material. So a lot of work was done to make these nice, short, quick pulses, but at some point, we reached sort of a limit to how well we could develop this technique. And that's what we see on this figure with the CPA, where it shows where this technique was invented. Basically, it sped up this process, and it was able to create a new technique, which now has been developed even further in these last 30 years. This technique is now used not only in the common examples, such as laser eye surgery and laser cutting and machining, which is how we can use these very narrow but highly intense pulses, but we also use it for things like looking at chemical reactions and some other more fundamental processes, because by having a very fast pulse, what you're able to do is you're able to look at things on a much faster time scale. Because fundamentally, when you're making a measurement, those of you who've taken a physics class with me, you remember me talking about invasive processes versus non-invasive processes. So basically, it's less invasive if you can do it more quickly. And that's essentially the idea behind wanting not only an intense pulse, but also a very quick pulse, is that you want it to be less invasive. So just to give a bit of a sort of context here, a nanosecond is a billionth of a second. A femtosecond is a millionth of a nanosecond. So this is 10 to the negative 15. So this process, this little chirped pulse, is 10 to the negative 15th of a second long. If you have a longer pulse, so if your pulse is happening over a longer time, it's more likely to heat the area around where you're making that cut, for example. Whereas if it's a fast pulse, you're still able to get those sharp cuts, for example, but it's happening fast enough that you don't get that sort of external damage. And based on the time scale is where you won't get those, what is shown in this diagram as a shock wave, but basically there's a concept involving the timing. It's related to the Heisenberg uncertainty principle, for those of you who know a little bit about that. But basically, if you can have it happen quickly, it's not going to perturb the things around it, essentially. So again, it's hard to really go through all of the details in 10 to 15 minutes, but hopefully this contextualizes it a little bit. Hopefully I've been able to give you a bit of context so that you can then go forward, learn more about this if you wish. If anyone wants to talk about it sometime, I'm in Huggins Science Hall, and I'd be happy to see you anytime. So thank you very much for your time.
So, my name's Elizabeth, and like Anna, I was asked to speak a little bit about the work of one of these Nobel Prize winners. And I will say that it is for sure daunting to look at their body of work and say, okay, yeah, I can talk about that in 10 minutes. So I wanted to start today with the conclusion, just in case it got lost in the mix and the real main point I didn't get to. So here's, it's actually from the Nobel Prize documentation of scientific information that was given out. And they say a main conclusion emerging from directed evolution, which is what Francis Arnold won the Nobel Prize for, is that enzymes can indeed be tuned to catalyze new reactions and to reactions very different from the ones catalyzed by nature's own enzymes. So direct evolution has widely expanded the repertoire of useful biocatalysts. The evolved enzymes offer efficient and environmentally friendly alternatives to metals and organic catalysts in chemical and biotechnical industries. So what does all that mean, and why is it important in chemistry and other fields as well? So the first thing I wanted to do is really remind anybody here about what a catalyst is and how important it is in chemistry and all kinds of different fields. So if you have a chemical reaction, something like this I have here, where you're going from reactants to products, a lot of the time these reactions require an energy input to be completed. So you have to put energy into the system, and then it takes time for the reaction to occur. You can circumvent some of these reactions and the energy it requires by using something called a catalyst. So this is something that allows the reaction to go quicker, but is not used up in the reaction, so you get it back in the end. So a reaction something like this, you might change the pathway that you're taking and reduce the energy that's required for the reaction to happen. So often it speeds up reactions, it requires less energy, which means it's very advantageous, especially if you're making industrial chemicals or commercial chemicals that require a lot of energy and a lot of time. So energy, a lot of the time, is money, and so if you can reduce costs, then it's very attractive. So this is something that happens all the time in a lot of chemical processes, in industry and commercial processes, in lab if you're doing some sort of synthesis. And it's because of that reason, there's all kinds of different fields based on catalytic chemistry. But it also happens in our own bodies. So if we look at macromolecules like this, different proteins, which can help speed up processes in the body, these are called enzymes. And this particular example is an enzyme that converts starch into sugars in your body. And so enzymes, while really useful in a lot of industries and chemistry, are happening all of the time in our own bodies, and so they're really important to a lot of the system, the metabolic processes that our systems undergo. So for our bodies to function the way we want them to, we rely on enzymes like this to speed up reactions so that they happen in timescales that our body needs them to happen in. So in saying that, enzymes really are crucial for how our bodies work. They're crucial for metabolism. And a few key points here to remember on how they work. If you have an enzyme, like here in this gray box here, they have something called an active site. So it's the part of the enzyme that actually goes and attaches to whatever you want it to, which in this case, we're calling it a substrate. So it has these active sites that are very specific, and in binding to different substrates, you'll have very particular reactions occur. So there's parts of the enzyme that are really important for specific reactions that we want to see happen. So in doing this, you'll bind them. In this example, you'll form products, so that's the two colored ones on the other side, and then you'll get back your catalyst, which you can then reuse for more reactions. So in saying that, you have this active site. There's a few key things here, and this is going to come up in a few slides down the road. So if you have a protein structure or enzyme structure like this, it's made up of a lot of molecules and a lot of bits to it. And the part that actually binds to the substrate is only a small portion of that. So there's only a small portion that's actually going to bind to the molecule you want it to. And then from that, there's even smaller bits that are responsible for that catalytic activity. So while you might have a large molecule like this, you really have to focus in on small parts of it when you're talking about speeding up the reaction and performing that catalytic behavior. So I guess the question then becomes, well, if these enzymes are so great, our body is working, all these really important reactions are occurring, well, what if we want them to do something else? Can't we just build more enzymes, build an enzyme that we want so that it's doing what we want it to do? And the answer to that, I think you have to take a step backwards and remember what these enzymes are made of. So if you go back to your biology or your biochemistry and you think of amino acids, there's 20 common amino acids that we usually talk about. And if you look at these molecules, I don't know if you can actually see them. So you can't see them very well, so you'll have to trust me in that these are fairly small molecules. They're made up of maybe 15 or 20 atoms. And so if you're going to study something like this, it's very, I wouldn't say it's easy to do, but it's very reasonable. They're a nice small-sized molecule. These amino acids come together to form longer chains of peptides, and so you build up these amino acids together, you form these peptides, and then with long chains of peptides you can form proteins. So once you get to these enzymes, these protein structures, they're actually really, really big. And so they're made up of thousands of amino acids. And so going to study them and studying all of the particular interactions that you can possibly have with a substrate or some other molecule becomes much more complicated. So this question of why don't we just build the enzymes we want, well, they're made up of thousands of amino acids. It's really difficult to do that and to do it really well. So it's hard to know how to put them together in the right way. It's hard to know how to put them together to get useful products or properties that you want. And it's hard to predict changes. So if you're going to change an enzyme that you already have to do some mutation to it, it's hard to predict what changes you'll have because of that mutation. So this brings us to Frances Arnold and the work that she has been doing. Her solution to this is not to build up the enzymes from the bottom up, but rather to copy a design process that's already out there, evolution, nature's design process, to build new biological things. So there she's taking something that's already happening in nature and applying it to the work that she was looking at. So this brings us to what's called directed evolution, and the workflow that was developed by her and her coworkers is really quite simple on the process. We're not going to do a deep dive tonight. That would take many, many hours. So basically, if we go through the 5 steps, you begin with an enzyme that has some of the desired properties that you're looking for. So it might not work really, really well, but it has some aspect that's of interest to you. The second thing is then to take that enzyme and introduce random changes. So to introduce these mutations to it to see if any of those have better activity or better function than what you initially started with. So the key here is to produce a library of different enzymes, and this library would be based on your molecular insight, the knowledge that you have about those structures and how they work, and some element of randomness as well to it. So trying as many different options as you can. The third bit is then identifying some selection criteria. So what is it that we're looking for? How are we going to know that that's working? And then taking that selection criteria, so whatever it is, okay, now we have better activity, picking out the enzymes from your new library that increase the activity that you're looking for, and then create new DNA sequence libraries around that selection. The fifth part is then to iterate to reach your target performance. So keep going through the process, taking the new enzyme that has those mutations that work well, and doing the same thing over again. So introducing new mutations, selecting again the ones that work really well, ditching the rest of them, and going through the process a number of times. So visually, I know it's small, but we'll try. So here, you'd have those mutations that you entered into your DNA to perform these enzymes. So now you have a lot of different enzymes that include those mutations as well. Then you'd test through them to find the ones that work really well for the selection criteria that you are interested in. The ones that don't, you can put them aside, take those ones that do, and go through the process again. So this has 3 main steps to it. The mutagenesis part, which is adding that variation. The screening process, which is assessing the fitness of the different enzymes that you've created. And then gene amplification, so going through the process and doing it again. So this directed evolution, you could call it natural selection at warp speed. So this is a really important point here, is that you're doing something on a time scale that's much different than nature does it on its own. So taking these enzymes, going through and cycling through and iterating to find increased activity. Okay, so directed evolution process allows us to do a lot of different things. I'm going to provide a few examples to you now, but really it allows you to identify variants in your enzyme. So find things that have higher affinity or selectivity for a different target that you are interested in, and mapping out those requirements. It can also lead to useful therapeutics, and there's lots of applications in other fields as well. So a few examples. So this is where I'm like not taking the deep dive, but we'll do a few little things. So in this example, this is subtilicin, and Arnold here was interested in finding enzymes that could be used in organic solvents. So typically, an enzyme like this would work really well in a water-based solvent, but would be denatured in organic solvent. And so in this case, through going through the DE process, they were able to create an enzyme that cleaved peptide bonds in organic solvents without being denatured. And through 4 rounds of mutagenesis and screening, they found an enzyme that had 256-fold higher activity than the one that they started with. So this has a lot of applications, especially if you're looking at organic synthesis and working with organic solvents to catalyze reactions there. A second example, looking at carbon-silicon bonds. So carbon-silicon are very common naturally occurring atoms. And they're common in human-made chemicals as well, but not in biological systems. So in this example, what they were able to do was find, take these heme proteins that are able to catalyze non-natural carbene insertion reactions. So basically, finding an enzyme that would catalyze the formation of these carbon-silicon bonds. And I didn't write it here on the screen, but I've got it down on my paper here. I think what it is that from the initial enzyme they had, they found one that was 40 times more efficient than the one that they had, and 15 times better turnover than any non-enzyme-based carbon-silicon catalyst. So what they were able to do really there is expand the type of catalyst that they were looking at for this particular reaction. Of also important note here is that something like this in using enzymes is an environmentally friendly route and highly efficient for producing organosilicon molecules. So a lot of the time catalysts require the use of some metals that are not particularly environmentally friendly and are toxic. And so finding environmentally friendly routes like enzymes is very advantageous as well. So they were able to do that with this. The third example that I wanted to show you is one where actually this work was not done by Arnold, but their work in directed evolution inspired this study. So this is looking at the synthesis of sitagliptin, I think that's right, which is a diabetes drug. So in this case, what they were trying to do in the synthesis was find a catalyst that would improve the reaction that they were looking at. And the enzyme they started had the catalytic machinery, so it had all of the important parts to it, but it didn't have any activity towards the target. So in proving that, they went through this DE process, went through the iterative process 11 times. And by doing that, they were able to improve the reaction rate of this, the synthesis by 10,000-fold, or more than 10,000-fold. And they found 27 mutations were involved in that. So in going through this process, and really, I guess, increasing the time or increasing the time scale that you're doing this at, they were able to find improved reaction rates for this drug, which is going to probably, or probably already is, affecting people's lives greatly. So some other notable results that came out of her work. So thermal stability of enzymes as well. They showed that DE can produce single enzymes with high catalytic activity at both high and low temperatures. So natural enzymes often will work in low temperatures, or they'll work in high temperatures, but not both. And so she was able to show that you can produce these enzymes that do that. Also showed increased activity and stability for different pHs of enzymes and use in commercial processes as well. And finally, although not finally, it's just all I'm going to talk about, created new activities, so enzymes that created molecules that otherwise might be difficult to produce. So in this case, some strange cyclic hydrocarbons. So what's the impact of this work? Well, there's lots of them. If you go back to what I talked about with catalysts, all kinds of commercial processes, chemical processes, reactions, synthesis, drugs, pharmaceuticals, all rely on catalytic reactions. And so being able to optimize and redirect enzyme function is going to affect all of those processes that are looking towards different catalysts or new catalysts to work. So there's improved and reshaped enzymes for many chemical reactions, and as I said, applications in organic synthesis, industrial processes, pharmaceutical industry. There's also contributions towards green alternatives. So like I mentioned, going from catalysts that might not be environmentally friendly to something that is, like an enzyme. Biofuel processes work there, and then protein design optimization. So there's lots of impacts there. I will also mention, so this is impacts directly in the field and when you're talking about catalytic chemistry, but anything like this, I think it's a big body of work, and so Arnold's work has impacts elsewhere as well. So I'll quickly mention here that her work, although it's a chemistry Nobel Prize, her area was in mechanical and aerospace engineering as an undergraduate degree, and her graduate degree was in chemical engineering. And anybody in chemistry now, I think if you look at the field, it is changing really a lot. Every year it's different fields popping up and different sciences coming in and working together, so a lot of integration between different subdisciplines. And I think somebody like this who comes in and maybe has an engineering background and talks about all of these biological applications or biochemistry or ways to improve industrial processes or organic synthesis is making big contributions to the field itself. And then finally, in preparation for this, I was listening to an interview that Frances Arnold had done, and I think the question was something like, well, what's next? What's the next question that you want to answer? And her answer was the following. So this is what she's interested in answering next. How do you evolve innovation? How do you get to a whole new chemical activity that you don't know already existed? How can I evolve a whole new species of enzymes? These are huge questions, but I think, and I hope you agree, that it's amazing to have people actually asking these questions and putting some time and putting their work and their life into trying to find answers. So with that, I'm going to ask Suzie Currie to come up to do the next bit.
I don't follow instructions well, clearly. So specifically, what does the future hold for women in science and engineering at Acadia? It's a big question. So we'll try to get there, and I'm going to try to get there with your help. And I think if you'll indulge me, to maybe get there, I want to talk a little bit about my past, present, and future. So as many of you will know, I'm an Acadia grad, class of 1991. And while I was here, I didn't have any female professors in any of my classes except one. And it was an elective that I took in family law. And I didn't really think about that until very recently, which is also interesting. So I really wish I had some of the wonderful women we've heard from this evening in my classes when I was at Acadia. But what I did have when I was here is an amazing mentor. I had many amazing mentors, but I'm going to highlight one here, and this is Dr. Dan Taves, who is my honors supervisor. And I had him in third year, animal phys, and then he was my thesis advisor. And when I was thinking about this talk, I thought about maybe 3 things I want to highlight, or 3 criteria that I think are important for our success moving into the future. And the first one is the importance of excellent mentors. And I can't say this enough. They may be women, they may be men, they may be kids, they may be grandparents, they may be your parents, they may be friends, they may be relatives, but the importance of mentors. And Dan Taves was like this with all his students before me and after, really instilled this sense of curiosity and really didn't talk about barriers. There were no barriers as far as he was concerned. Now, that's not necessarily true, but basically, do what you're passionate about. Do what gives you joy in life, in science, and just go for it. And so that was really the ethos that I felt here the whole time at Acadia, despite not having any female professors, which I still can't get over. So I went on to do grad school. Again, I had no female professors. In my master's and PhD, we didn't have to do courses, but my advisors were men, and they were great. Again, you can do whatever you want to do. But I have to say I had a very good mentorship in terms of the graduate student community where I was involved. And we mentored one another, really, in terms of gender issues. And it was really only into my PhD that I started to become aware and deliberate about my interests and my observations about gender differences in science and also in leadership. And then I went on to the University of Cambridge for postdoctoral work, and this was a really eye-opening experience for me. And largely because I found another mentor, Dr. Nancy Lane, an amazing person, an amazing female scientist, has an OBE, a Cambridge cell biologist who did a PhD at Oxford and is from Halifax. And in 2006, she actually won the Nova Scotia Discovery Centre Hall of Fame Award. So because of our Nova Scotian connections, because I'm also originally from Nova Scotia, from Cape Breton, and we have friends in common, she really took me under her wing when I started postdoctoral work in Cambridge. And in addition to being a brilliant cell biologist, she was also tasked by the Royal Society to lead a very important project that was launched in 1991. And that's the Athena Project, which may be familiar to some of you. So this launch, again, it was during the time that I was in Cambridge. The aim was the advancement of women in science, engineering, and technology, specifically in universities, mostly in higher education. And the other important aim was to make sure there was a significant increase in the number of women recruited to top posts. And I just want to echo what Dr. Newman said, which I also believe very strongly, is that representation matters. And it has not been lost on me. In fact, I'm deeply honored and thrilled to be the first female Dean of Science, which is also a little bit shocking because it is 2018. But I'm happy to do it. I'm going to go for it. But that representation does matter, and the Athena Project, a huge goal of that was to increase representation, specifically at this time, of really women recruited to top posts in higher education. So that project was initially meant to last 4 years, and it lasted a little bit longer, and Dr. Lane was instrumental. And it was during that time in Cambridge, because there were a lot of things happening, there was a lot of momentum. So I had the opportunity to travel across the UK, attending workshops, networking events. And again, this is when I think I became, I don't want to say aware, because I was aware of it, but I guess it became more engaged in looking at diversity, gender differences, again, not only in science and engineering, but also in leadership positions, specifically within universities. So that Athena Project then morphed into the Athena Swan Charter in 2005. And Swan stands for Scientific Women's Academic Network, the acronym. And here, basically, the idea of diversity and representation was broadened, I think appropriately. So the idea of the Athena Swan Charter was recognizing advancement of gender equality, representation, progression, and success for all. And this is really important, again, emphasizing that importance of representation and diversity. And I bring up this Athena Swan Project specifically, and this is 2005 in the UK, because fast forward to the present in 2018, and as some of you will know, there is now, just as of a few months ago, a pretty strong initiative within Canada to launch a Made in Canada Swan Project that reflects Canada's unique reality. And this is really important and significant. Again, it's taken us a while to get here, but basically it was Kirsty Duncan, who you know is the Minister of Science and Minister of Sport and Persons with Disabilities. Everyone deserves to have their voice heard and to be valued equally in the worlds of science, technology, engineering, and math. The Athena Swan Initiative is key to making this happen. And there have been workshops across the country over the early in September and October, to try to get this initiative off the ground. There's been federal monies in the 2018 budget to put towards this project and to really pay attention to equality, diversity, inclusivity, specific grants targeted at making this happen. And this is hugely important, I think, for all of us in science, engineering, and technology, and in higher education in general. So, yay, it's happening. So when you see these things come up, when you are asked for feedback, which we have been asked about the Canadian Athena Swan, please give it. Get involved, get engaged. It's important for our future. So then thinking about our future, and as I said, one of the things that I think is really important is the importance of having great mentors. Also, I think the value of diverse perspectives, experience, and values. Hugely important. And this again gets back to the representation. We have to have different ways to do things. There's not only one way to do science and engineering. We need to explore and express this diversity. And I think we see this particularly in leadership roles, because we need to have diverse people in leadership roles to affect change. We do things differently. We need to celebrate our differences, and we need to lead in different ways. We do science in different ways. Our diversity and our differences, I think, is what leads the creative process in many ways. So for me, this is a really important thing. And again, me being here is very meaningful for me because of this number 2. And then the third thing I'll say, which again touches on what Dr. Newman said in her opening remarks, recognition is huge. In my experience, with my friends and my colleagues and in my family, as a woman, self-promotion is a big no-no. Oh, don't brag. Don't tell anyone what you're doing. This is just something, and maybe it's just me, part of my culture, but even in the students, I've supervised many undergraduate students, 2 of whom are sitting here in this canoe. Avery may recognize some of them in the back. So we're not that great at it, but we don't necessarily have to be. I'm not here to say, yes, you've got to self-promote, you've got to tell everyone how wonderful you are and all the great things you're doing. I don't think that's true. Unless that comes naturally to you, then I think go for it. But as a community, we have to be better. We have to be better at the recognition piece, at elevating, at celebrating, and at promoting each other. So this is where the mentorship and the networks, I think, really come in. And I do think this is an important part of our future. We have to elevate. We have to promote. We have to recognize. And the 2 Nobel Prize winners that are women this year, yay, it's going a long ways to that. And what I did want to add, which I didn't really realize until I heard the talks earlier, is that these women are being recognized for work they did as young women. As young women. I believe Donna Strickland's discovery was her first publication. Okay, it's her first publication. And I see too with Frances Arnold's, some of her citations are from 25 years ago. So they were around some of your ages, right, when they made these wonderful discoveries. So keep that in your mind. You don't have to do 30 years of blood, sweat, and toil, to do wonderful, amazing work. So keep that, but maybe after 40 years of blood, sweat, and toil, you could still do amazing work too, right? So it doesn't all have to happen when you're young. So for me, this elevation and recognition and celebration piece, again, is an important part of our future. So what does this all mean for us? I've kind of separated this out into passive and active. And by passive, I don't want you to get a negative connotation. But the kind of passive things is that we're doing it already. So if I just use myself as an example, so now I'm here as the first female dean of science, so that's a plus. But I guess just the things that we just do all the time. It's important to be true to ourselves and our own values and be ourselves and don't try to be like other leaders that have gone before us or other students that have gone before us or other academics that have gone before us or department heads or deans. We have to be ourselves. And how we make decisions is different. And that's okay. How we run meetings may be different. How we communicate will be different. And I think we have to not try to fit into some sort of mold that historically we've seen as the way to do science, the way to lead, the way to be in higher education. What we value is different, and that's also okay. And I think it's important to make that clear. And then there's the active side of things, which I'm going to need a little bit of help on from you. So wise events like tonight, this is a way, right? This is a way forward, I think, for everyone. Change the rules. Again, we don't have to fit into a mold that has gone before us. Be true to ourselves, be true to the way we lead, how we do science, how we're creative, how we interact, how we network. Change the rules. And support each other. It's huge. Support, celebrate, elevate. I can go on. Champion, advocate, nominate. That's the other thing I've noticed in my career as an animal physiologist. We've got a few, not very many, but a few women that are in professorships. But over and over again, all the awards are always, or I should say, are never going to women. And then you look, it's because it tends to be, at least in my field, that the men were nominating other men, and they knew them, they were their students, all legitimate. But we got to get in there, and we have to start nominating, or do more of it if you're already doing, way to go. But this is really important. Recognize, like the Nobel has seen fit to recognize 2 women this year in the prize. So I think this is important. Yeah, I just wanted to put that crown up there. Champion. So the question, I think that Professor Anderson posed, what are the most effective ways to support us at Acadia? And I have some thoughts and I have some ideas, but I think I have maybe a couple of minutes. Someone, do I have a couple of minutes? To ask you, because this is important that I know, what are some things that we can do to support each other, or things that I can do or ask someone else to do to support us as a community here at Acadia? And I want to hear from staff, students, faculty, offspring of faculty. What can we do? What do you need? I mean, we've talked about past, present, future. How do you think it's going? There are more female professors at Acadia since I was here in the late 80s, early 90s, so that's a plus. There's increased representation. We have these wonderful WISE events and a wonderful community of leaders. But what comes to your mind? What do you think are the top things? What are the top 3 things that you need, or that you're looking for, or that are important to you? What do you value? How do you feel supported? There's got to be something. It's in your wish list. Don't be shy. Great. Do you want to speak into the mic? It's just fun.
I really resonated with the last thing you said, especially in terms of recognition, in terms of appreciating the people who are doing amazing work and encouraging people who should put their ideas and make them into future amazing work. So I think a good idea, maybe a good idea, would be a newsletter of just recognition, whether that's students, whether that's staff, research, just kind of a very short newsletter, maybe weekly, maybe monthly, of this is the amazing stuff that's going on by the women at Acadia, and just by constantly throwing that in our face, we're encouraged. But there are people in this community, in this 2-mile radius, that are doing amazing things. And that means either I can go out and find a mentor, or I can mentor someone else. Yeah. I think that would be maybe a good idea.
That's a great idea. That's a great idea. Thank you. And awareness, I think, as you say, awareness so we can support and mentor and nominate and celebrate. Wonderful idea. First newsletter, on you. No, I think that's great. Infrastructure, I'm just trying to, and I'm looking at Alice actually back who I might pinpoint. Just the things that could change in the university that could support diversity.
I'd like a child care center.
Child care center. What do people think of that? Like a daycare type, like a university affiliated daycare? Yeah. Alice?
Okay, so I'll say something. So can I add to that? So
Sure.
I think advocacy around childcare and daycare is awesome. I think also it would go a long way to not just framing it as a women's issue.
Agreed.
'Cause
Yes.
Yeah. So it's important, but
It's a diversity.
But not only for women.
Yeah.
Yeah.
I think that's sort of, I think too, when I was looking at the Athena and the Athena Swan, really, we're talking, this is a women in science and engineering event, but really it's about diversity and inclusion and equality, and I think that's how things are moving. And it's great to see a diverse audience here too. What else? What do you need? What's on your wish list? This is Diane. Do you want the mic?
I think it would be nice to have a little bit of funding available. You talked about the important work that people can do even as young scientists, but sometimes we need a little bit of funding.
Yes,
and
we do.
Sometimes it's difficult to get those large external grants, and there are internal grants that are available for professors. Sometimes it's supporting the students, but funding for students so that they could apply the wonderful HSRAs, but that supports money for the students, but not direct cost of research.
Right.
So having
Grants.
something where it's sort of like, here's some money for the summer, and here's $500 or $1,000 that you can use to pay participants, you can use to buy the equipment you need, that sort of thing.
Yeah.
And then also travel. I just sent an email today to students, about 10 students I've mentored over the last few years, saying, who wants to go to such and such conference? It's going to be in Halifax, it'll be a great opportunity. I will pay what I can, but I don't have large grants. And some of them may not be able to go because they don't have the funding. We have small amounts of departmental funding, but there's not that much at the university that funds student travel conferences.
No, that's a great point. Yeah, so student travel and student grants. I noticed a faded sign on the ground floor of Huggins when I first got here. It's called the Science Discovery Fund. It's like, what's this? And not many people knew, and I had to do some digging. I think I might know now, but it's these kinds of things, right, that can support, and so talking to advancement, and we as a community, not just me, talk to advancement about, I think this is critical, right? Support for students, not only the stipend, but travel, research grants, and then you own it too as a student. Yeah, that's a great suggestion. Anna?
And I think going back to, bursaries for students as well, because I think often students who have a very strong leg up to begin with are more likely to get the scholarships, especially the entrance scholarships. And I think bursaries and then scholarships that come later will increase student retention, but also I think will enable people who may not otherwise be able to attend because they have to pay for childcare or because they otherwise don't have access to funds. I was going to say, to me, that's an equity concern.
Yes.
And I think that would be great to target that with students in science, particularly women.
I love it. I hope somebody's writing all these ideas down. What else? Jason.
Probably don't need that. Sure. I was just going to say engaging in the community more broadly. So I was thinking of kids that all of the doctors they have are women. And it's a perfect example of how, like, for them, a woman doctor is just going to be normal. Now, I hate putting more pressure on my female colleagues to then be the ones that go out and engage in the community, but I think the more that students, kids, high school students, whatever, see women scientists, if that is a barrier that they even see, it's not going to exist as much. But again, I realize usually female colleagues already are taking a bigger burden of service and things like that. Just statistically, that seems to happen. So I hate to say do more of that kind of stuff.
But do more of that. Yeah. No, that's a very good point. That's an excellent point. And some of you may have seen this. It was on, and we're winding up, on Facebook recently, just on that point. Little kids were asked to draw a female scientist, and they've been doing this for years, right? And always it was the old guy with the glasses and the white coat and the fuzzy hair. And then I think it was just last year that it was a young woman in a garden with a microscope and braids with her field notebook. Yay! And that was from little tiny kids. But it's my time to wrap up, and the next speaker, is Wanda again.
All right. I want to thank the organizers for including me in this evening, because I know in the world of literature how important it was for female writers to have foremothers and mentors. I think Virginia Woolf said everybody should lay flowers on the grave of Aphra Behn. So this idea of paying it forward, and the same is surely true of science, as we've heard tonight. And I'll never forget when my 3 young daughters were very young. We were at Point Pelee National Park, and we happened to run into Roberta Bondar, and we pointed her out as Canada's first female astronaut, and our eldest daughter said, "Why aren't you wearing your spacesuit?" And my daughter, and anyway, without missing a beat, Dr. Bondar said, "It's Casual Friday." So that's the perfect kind of mentor. So I thought it would be appropriate tonight to just refer briefly to American marine biologist Rachel Carson, and people will know her book Silent Spring that helped launch the modern environmental movement. And in her acceptance speech of the National Book Award for The Sea Around Us in 1952, she said, "The aim of science is to discover and illuminate truth, and that, I take it, is the aim of literature. It seems to me then that there can be no separate literature of science." She also said in this same acceptance speech, "The winds, the sea, and the moving tides are what they are. If there is wonder and beauty and majesty in them, science will discover these qualities. If they are not there, science cannot create them. If there is poetry in my book about the sea, it is not because I deliberately put it there, but because no one could write truthfully about the sea and leave out the poetry." So the poem I'm going to read tonight is called String Theory, and I do not pretend to understand it whatsoever, as I would need, the kind of explanations that we've gotten tonight. But I think as a poet, I do understand curiosity and the power of making connections. And as to refer back to Adrienne Rich, with whom I began, she said, "We might hope to find the 3 activities, poetry, science, politics, triangulated with extraordinary electrical exchanges, moving from each to each and through our lives." So, string theory. And this is a glosa, which begins with 4 lines from another poem, which those lines are repeated throughout. And the other poem is T.S. Eliot's Little Gidding, and the lines are, "The children in the apple tree, not known because not looked for, but heard, half heard in the stillness between 2 waves of the sea." The poet says, "In the end we will arrive where we began and know the place for the first time. Everything is connected to everything else. We think we operate in 4 dimensions, but there are several we can't even see. And here in this valley of orchards, I relearn the branches of my youth, recognize the curious climber as me, and the children in the apple tree. The way to glimpse elementary particles is to pretend they are points in space, interacting on the stage of gravity, with strings holding them together like a net to catch all reality. Just as art often includes a door, we do what all scientists and poets do, use what we know to learn what we do not, aware that the explorer misnames the shore, not known because not looked for. I walk on the wind-blown dikes where dérangement still endures, and the tide rushes in with the force of all the rivers in the world. I know of no better way to heal the hurts we carry like an illness, cruel and chronic though kept at bay, whispers of the past, drowned by cries of gulls, their squawk and shrillness, but heard, half heard, in the stillness. The sea's slender fingers slide across strings of knotted kelp, tangled against the rocks, to play a planxty on the harp of who we are. We hope to recover dimensions lost along the way, but there's no guarantee. Whatever the ocean hurls at us, pebbles or mermaid's purse, rags of foam or refuse, we pan the stars from the debris between two waves of the sea.
Hello, my name is Yvonne Lyon. I'm a third-year biology and kinesiology student at Acadia University, and I'm the current student body president for WISE, Women in Science and Engineering, this year. I'd first like to say a massive thank you to everyone who spoke before me and everyone who helped organize this behind the scenes, and of course those that inspired this event, so thank you. I'd also like to share something that Dr. Muckford told me while promoting a WISE event in my first year at Acadia in an intro to biology lecture. Women in science is not a women's issue, it's a science issue. I thought this was such an important quote because it is a simple matter of fact that science needs women. Women, as we've noted today, are responsible for amazing discoveries, whether they are recognized for that or not. If you think of all of the brilliant designs within this world, it's incredible to think of how many more discoveries we would have if women were given the same opportunity as men. According to the UN, on average, globally, the researchers in the entire world, only 29% of those are made up to be female. And only 35 people reaching a higher education in the STEM fields are female. As a result of these drastically different numbers in comparison to men, I thought I'd reach out for some encouragement to the people in this room. As a result of me reaching out, I was able to gain advice for us from 4 different Nobel Prize winners who are all women. 2 past Nobel Prize winners and 2 of the ones that we currently recognize today of the 2018 female winners. The first one I have here is a French woman, Dr. Françoise Suzie. She's a virologist who won the Nobel Prize in 2008 for medicine and physiology. She did work in retroviruses for the purpose of discovering a human immunodeficiency virus. She gave the advice for women to live your passion, to be dedicated to others, and to create a better world, and to be a strong, persistent fighter to overcome your situation. Secondly, Dr. Adrienne gave us advice. She is an Israeli chemist who won in 2009 the Chemistry Nobel Prize. She won for her work in understanding the mapping of the structural RNA. What she did is she used X-rays and crystallography in order to make antibiotics more accessible. She made, through her understanding of the mapping through structural RNA, she made antibiotics more accessible and cheaper to manufacture, so they're more accessible to people of a lower income. She gave the advice to know your own truth and to seek advices within yourself and to be strong as a female in science. To bring us up to current standard, as we described, Dr. Donna Strickland, a Canadian physicist, won the Nobel Prize for Physics in 2018. She gave us the advice to know your strengths and weaknesses and to always play to your strengths. And to do it is fun or interesting or exciting, because then you will work hard. And she gave us the advice to always be grateful for every single opportunity that comes your way. Finally, Dr. Frances Arnold from Caltech, an American who won an award in chemistry, gave us the advice to find something you enjoy every day, even if you take some pivots, and that there is no one formula for success, and to take advice selectively. And if there's one thing that I'd like you to conclude from all of these advices and the entire presentation is that women in science can be scientists. So when you look in the mirror every day while you brush your teeth or whatever have you, I want you to understand that you are what a scientist looks like. That you have in total capability of achieving amazing things because women are incredible and people in total are incredible, and we all can fight to push for a more advanced and better world based on our research. Thank you. And a networking session is going to break out immediately after this with the food. Thank you. This precedes our talks.